I should like to extend to participants in this conference my warm greetings and to express my regret over my inability to be here in person. I'll start with a preview rather than what is traditional, a table of contents. Well, so here are some of the key points. What we're going to talk about is the issue of whether or not human-level machine intelligence is achievable. And my principal point will be that using the existing approaches, human-level machine intelligence is not achievable. So, what do you mean by human-level machine intelligence? Now, concretely, what do I mean by this? There is a machine M, and inside this machine M, there is a brain which has the characteristics of human intelligence. In particular, it can understand, it can converse, it can learn, it can reason, it can answer questions, and it can ask questions. So, how do we assess intelligence or machine intelligence? Well, one, in terms of everyday experience. We use systems like automated customer service systems in which when we call a particular organization, we find that we don't get a human operator, we get a machine. The machine asks you questions, and presumably it should have the ability to answer your questions. But in many, many cases today, you find that the system does not work well. So based on experiences of this kind, then, we come to the conclusion that we have not as yet achieved human-level machine intelligence. The other one is the famous Turing test, which was suggested by Alan Turing in 1950. And his test basically is the following. There is a curtain, and behind the curtain there is either a human or a machine. And you converse with whatever is behind the curtain, and at some point then you are supposed to decide whether or not behind the curtain is a human or a machine. And if you cannot tell whether it's a human or a machine, then that machine passes the Turing test. Now, my point is that Turing test is not really necessary because there is a very simple test that no machine can pass. Specifically, you talk for 2 or 3 minutes, and at the end, you ask whatever is behind the curtain to summarize what you said. Today, no machine will be able to do that. And then there is something else, which I call machine IQ. So we can talk about human IQ, but we can also talk about machine IQ. So what is machine IQ? What I mean by that is that you take a machine and you try to come up with the measure of the intelligence quotient of that machine. That we'll call MIQ. For example, you may have a camera, and then you ask the question, how smart is this camera? So there are differences between IQ and MIQ. MIQ is specific to a particular class of machines. So you cannot compare the IQ of a washing machine with the IQ of a camera. They're altogether different things. So at this point, we can, in principle at least, to come up with measures of IQ of some particular class of systems, for example, washing machines. And perhaps in 5, 10, 15, 20 years from now, when we go to a store and you see washing machines of various kinds, then you will see that every machine is associated with the MIQ of that machine to help you in your decision on whether or not to buy that particular machine. Now, so the principal point, as I mentioned already, is that using the armamentarium of present-day AI, which is a combination of logic, Aristotelian logic, and logic-based probability theory, we cannot achieve human-level machine intelligence. But in any case, achievement of human-level machine intelligence is a challenging task. So let's look at what we view as scientific progress. Generally, we start with perceptions. And we say that scientific progress, which we can expressly describe what we're talking about in numbers. For example, length, width, temperature, blood pressure, whatever the case might be. Now, what we do, or we should do, or we can do is this. We take a perception and we describe it in words. That is what natural language does. But these words do not have precise meaning. And so what we want to do then is to take those words and precisate those words and perhaps eventually come up with numbers. But generally, it is a very deep-seated tradition of according much more respect to numbers than to words. So what is the paradigm shift that I alluded to in the title of my presentation? Well, so traditionally, we go from unprecisated words or perceptions to numbers. Now, non-traditionally, we go from unprecisated words to precisated words. Now, what do I mean by precisated words? This is something that I'll discuss a little later. And counter-traditional is when we go from numbers to precisated words. Now, let me stress that, as I said already, traditionally, we go from words to numbers. Counter-traditionally, we go from numbers to words. So, it is the mechanization of the remarkable human capability to reason and converse with perception-based information that is one of the principal objectives of artificial intelligence. So we want to mechanize this ability, one of which is linguistic summarization. So humans can take large bodies of information, numbers, and summarize it in a natural language. We want to have this capability. Now, when we talk about summaries, we usually talk about summaries of a story or a book or of a report or something like that. But we can extend the concept of a summary. In particular, we can talk about summaries of mathematical objects. We can summarize a function. So what we do for this purpose then is we take x and we take y and we granulate. And I'll describe that in greater detail a little bit later. X and y. So we have small, medium, large. And the triangles that you see there, these are so-called membership functions. So small, medium, large are fuzzy sets, and the triangles are the membership functions. So we do that, and then what we do is this. Then we say, if x is small, y is small. If x is medium, y is large. And if x is large, y small. And so what you see there at the bottom on the right side is the natural language description of that function. And that is what we would call a summary of the function. Now, if you look at the applications of fuzzy logic today, you find that in most of the applications, there are many, many, for example, digital cameras, most of them use fuzzy logic. Washing machines use fuzzy logic. Automobile transmissions use fuzzy logic. Hybrid engines use fuzzy logic, and so forth. In almost all of those applications, what is employed is what I call fuzzy logic gambit. So what is it? Now remember that gambit in chess means sacrifice of a piece to gain advantage further down the road. So you take the function and you summarize it. So you impreciate it. But then what you do, you preciate the meaning of words in the summary. You preciate what you mean by small, medium, and large. So it is a gambit in the sense that initially you impreciate, but later on you preciate. And in that way you get significant advantages. And the reason for it is that precision carries a cost. So when you impreciate, you reduce costs. So generally our decisions are based not on complete information. Our decisions are based on summaries of information. When you buy an item and you look at the catalog, what you see in the catalog is a summary of characteristics of the product that you want to buy. When you want to take a job, the same thing. When you're being hired, the employer looks at your resume, etc., etc. So here we are mimicking what humans do with great success. Now, so what we can do then is this. We take a system and we construct a model of the system. But instead of using a mathematical model, we construct a linguistic model. That is, we describe the behavior of the system in a natural language. And an example of this sort of thing is YAMAKAWA'S inverted pendulum. So, inverted pendulum is a test problem. It's a well-known problem in the realm of control, and classical control theory can stabilize an inverted pendulum. So you have something like what you see on the cart moves back and forth, and you want to stabilize the inverted pendulum. Now, so if you use classical theory, what you have to do is to take the differential equations and apply stability theory to these differential equations. That would be the traditional approach. But what Yamakawa did, he's a professor in Japan, in 1987, he applied fuzzy logic. So he granulated two state variables, theta, which is the angle from the vertical, and theta dot, which is the derivative of theta. So what happens then is this. He constructs a collection of rules. Now here it is a table lookup representation of the rules. So on one axis you have theta, on the other axis theta dot. So you say if theta is large and theta dot is large, then apply a big push, and so forth. So these are the rules. There are approximately 10 rules. And these 10 rules can be constructed by somebody who has no mathematical education, training whatsoever, and knows nothing about stability theory, control theory. So what Yamakawa showed, and it is a remarkable point, is that you do not need differential equations, a knowledge of stability theory to stabilize an inverted pendulum. And this is one of the contributions of fuzzy logic. That is, construction of simple models, linguistic models of complex systems. Now, here is a video clip that shows Yamakawa's inverted pendulum.
The most typical case of parameter changing systems to be controlled is the inverted pendulum on which a living animal is moving around. The mouse is moving around on the table fixed on the pendulum, and we cannot expect the movement of mouse. Therefore, we cannot establish a mathematical model of this system, and thus we can hardly control the system by a mathematical way, as well as wine glass stabilization. When the mouse is moved to the right or the left, the pendulum is moved to the same direction by the fuzzy logic controller to compensate the attitude.
So we have a mouse on top of the pendulum. It would be very difficult to write differential equations for that kind of a system. At least I could not do it. So we are going to have the next video clip. Hopefully it will work. And so what you'll see there is a remarkable achievement by Chinese scientists and engineers, 2002. And in that case, what we see then is stabilization of quadruple pendulum, a pendulum that consists of 4 segments joined together. So this is a much more complex problem, and humans would not be able to do that. So Chinese scientists and engineers have shown that they can do it using fuzzy logic. And that was a remarkable achievement. I'm sorry, the video clip does not work.
经过数年的努力，经过对理论以及实务的不断完善，在2001年，李洪金教授领导的复杂系统实时智能控制实验室，采用辩论域自适应模糊控制，成功地实现了3级倒立摆的实物系统控制。
Actually, this
大家看，这就是个3级倒立摆，所以3级倒立摆呢，就是有3个摆杆，把它连接起来，这之间连接都是自由连接，可以自由活动的，那么倒立摆呢，就是要把它倒着立起来，使这根3个杆子呢，把它稳定起来不倒，那么控制这个问题是相当困难的，我们这个3级倒立摆呢，不但能够把它控制起来，还可以走路，也就是说具有所谓定位功能。那么据我了解呢，世界上能够把3级倒立摆能够控制起来的不多，可能是1、2家，至多2、3家。
Actually, what you saw was a triple pendulum, but they have done it with quadruple pendulum. So the reason why I showed you this inverted pendulum is to show that fuzzy logic can be used successfully to solve certain problems which are either cannot be solved through the use of traditional approaches, or can be solved much more simply through the use of fuzzy logic. Now, fuzzy logic has been, and to some degree still continues to be, controversial. And when I described for the first time my idea of using natural language to deal with various kinds of problems, well, there are many, many people who reacted very negatively to this idea. And one of them was Rudy Kalman, a person who is a brilliant scientist, very well known in the realm of control systems, systems analysis, and so forth. And so what he said, basically, I'm not going to read what you see, but he said that, well, what Professor Zadeh said doesn't make any sense. And actually, what he said was much longer than what you see. But anyway, this is the gist of his criticism. And there are many other people who said more or less the same thing. But history has shown that those people were not right. They simply did not understand what fuzzy logic has to offer. So, as I said already, one of the principal objectives of AI is achievement of human-level machine intelligence. And progress over the past 50 years or so has been very slow. Why? Well, it has been very slow, and this is the point I'm trying to make, because there are many, many things that humans can do that are a matter of perceptions rather than measurements. And traditional AI has not come to grips with the question of how do you reason with perceptions. So when AI was born in 1956, there was a great deal of enthusiasm, and there were exaggerated expectations. I could spend quite a bit of time showing you all kinds of projections that were made that today appear to be ridiculous. But anyway, that was the climate of the time. There was an underestimation of the difficulty of mechanizing the many remarkable capabilities that humans have. Now, today, of course, we have a much better understanding of some of these difficulties. But still, there are people, many people perhaps within the AI community, who are predicting that by a certain time, for example, in the case of Kurzweil, 2029, we will have human-level machine intelligence. It will be very interesting to say whether or not he is right. But what I'm sure of is that if it becomes a reality, it will not become a reality through the use of existing techniques based on classical Aristotelian bivalent logic and probability theory. What have to be used are techniques based on fuzzy logic, and more specifically on what I call computing with words. So there are two remarkable human capabilities. One is, as I mentioned already, the capability to converse, to reason, to make decisions, rational decisions, in an environment of imperfect information. Now, imperfect information is information which, in one or more respects, is uncertain, imprecise, incomplete, unreliable, vague, or partially true. So humans can do that. And second is the capability to perform a wide variety of physical and mental tasks without any measurements and any computations. And an everyday example is driving a car in city traffic, heavy city traffic. Today, we cannot mechanize this capability. And it will not be or mechanizable through the use of existing AI-based techniques. So, as I said already at an earlier point, a natural language is basically a system for describing perceptions. So we start with perceptions, we describe them in a natural language, and then we go from natural language to perceptions. So we evoke perceptions. So the perceptions that are evoked or recreated, those perceptions are the meaning of what we see in a natural language. That's basically the way meaning should be defined. It's not the way meaning is defined in the literature of linguistics. So what happens then is this. As I mentioned already, in a paper which I published in 2001 in Artificial Intelligence, I took the position that the reason for this inability relates to the fact that AI has not come to grips with how to deal with perception-based information. And so my suggestion then was to take perceptions, describe it in a natural language, and then compute with those descriptions. This is what I call the computational theory of perceptions, CTP. Now, perceptions are intrinsically imprecise because they reflect the bounded ability of sensory organs and ultimately the brain to resolve, detail, and store the information. So when we look at somebody, we have a perceptions of that person's age, but we cannot tell exactly what the age is. We cannot tell exactly what the height is, what the weight is, and so forth. We do have a perceptions, but perceptions are intrinsically imprecise. So imprecision of perceptions is passed on to natural language. And that is why natural languages are intrinsically imprecise. And that is why traditional approaches to the semantics of natural languages don't work that well, because they do not come to grips with the issue of imprecision of natural languages. So what we need then to deal with natural languages is what I call computing with words. My first paper on the subject appeared in 1999. Abbreviation of computing with words is CW, and some people use CWW. So computing with words is based on fuzzy logic. So I have to say something about fuzzy logic computing with words, and so this I do in the following section. So the point of departure in fuzzy logic is the concept of a fuzzy set. A fuzzy set is a class with unsharp boundaries. A set is a class with sharp boundaries. So that's a fuzzy set. And if you look at the real world concepts, you find that almost all of them are fuzzy sets. the concept of beauty, honesty, close, far, elegant, whatever. They're all fuzzy sets. That is, those concepts do not have sharply defined boundaries. So how do you make the concept of fuzzy set more precise? When you use the concept of a membership function. A membership function associates with each object the grade of membership of that object in a fuzzy set. And this is what I described in my 1965 paper on fuzzy sets. The concept of a fuzzy set and the concept of a membership function. Basically, very simple concepts. Now, so in fuzzy logic, everything is or is allowed to be a matter of degree. And the degree are allowed to be fuzzy. So if you ask to what degree is Mary beautiful, you would be allowed to say to a high degree or small degree, whatever. You are not required to say to the degree 0.75. And usually these degrees take values on a scale from 0 to 1. So here is an example of how we precision the concept, middle age. So what you see here is a fuzzy set, its membership function. It's assumed to be trapezoidal. So from a certain age to a certain age, the grade of membership is 1. From certain age to the left of that age is 0. And then there is a transition period from 40 to 45, for example, where the grade of membership increases gradually as a function of age. So you have parameters here, numbers 40, 45, 55, etc. Now, what those parameters are depends on the context. What are you talking about? Are you talking about middle-aged scientists? Are you talking about middle-aged tennis players? Are you talking about middle-aged cities and so forth? So in general, we have context dependence. But in a particular context then, we can precision a concept through what I call graduation. Gradus in Latin means degree. So you assign degrees to that concept. Now, we have done that in a few cases, but not in many. But in addition to graduation, we also have granulation. So what's granulation? Granulation, in some sense, is partition. So we take an engine, and we consider its parts: block, head, crankshaft, pistons, rings, etc. Now, so we divided that engine into parts which have sharply defined boundaries. But let's do that to human body. We have head, neck, arms, nails, whatever. Now here, we granulated the human body. But the parts, the granules, do not have sharply defined boundaries. They're fuzzy sets. And let's take a specific example. I have a hand. Where does the hand end? Now, I give you three things: ballpoint pen, a chisel pen, and what I call a spray pen, which is sort of miniaturized spray can. And I say, show me, where does the hand end? Now, so you can use ballpoint, but this ballpoint pen would not really be a good match to what is your perception, because your perception of where the hand ends is fuzzy. It's not crisp. Chisel pen will do a little bit better. But what will come closest to your perception is the spray pen. With the spray pen, then, you say, this is my perception of where the hand ends. And this is what fuzzy logic does. So if you say, what is a hand? Then you use a spray pen rather than a ballpoint pen to define that. Now, so what we have then is this. we take something, let's call it PRECISIATED with E at the end, and we PRECISIATE it, let's say, through graduation, and we come up with what I call PRECISIATED. So there is a relation between the two. How good, how closely does the PRECISIATED fit the PRECISIATED? That's what we call cointension. So a qualitative measure of closeness at fit. So if I have middle-aged, and I give you that trapezoidal fuzzy set with some parameters, is that a good fit, to what you have in mind? Well, a measure of the goodness of fit would be cointension. So when we PRECISIATE something, it's not sufficient to come up with a PRECISIATED. That PRECISIATED should be cointensive. A PRECISIATED basically is a model of PRECISIATED. So it should be a good model. So in classical logic, you're using a ballpoint pen. In fuzzy logic, you use a spray pen. And an electronic implementation of a spray pen is what I call Z-mouse. So you have a computer, you have a screen, you have a mouse, but the cursor is not what it is normally. It is a fuzzy mark. And that I call a Z-mouse. And so here is a simple example. What is the probability that Robert is home at about at 6:15 p.m.? I have some information, which is question-relevant information. Usually Robert leaves office at about 5 p.m., and usually it takes Robert about an hour to get home from work. So what I do then is this. I use the Z-mouse. I have a scale, and that scale are marked approximately 5 p.m. Approximately, I represent a star 5. So that's a Z mark. And then I do the same for travel time, approximately 1 hour. And then I say, what do you mean by usually? Well, usually is a fuzzy probability. So on the scale from 0 to 1, I mark what I mean by usually. Then the system goes through the computations and comes up with an answer. And the answer will be a fuzzy interval. It will not say the probability is 0.73. It will not even say probability is approximately 0.73, but there will be an interval. So that is how fuzzy logic, and more specifically, computing with words, will work. Now, fuzzy logic has several facets, 4 facets, principal facets. One of them is logical. The other one is set theoretic. Another one is semantic. And the other, or epistemic. And finally, relational. So, as I said earlier, fuzzy logic is used in many applications. But in most of the applications, what is used is the relational facet of fuzzy logic. More specifically, the concept of a linguistic variable and fuzzy if-then rules. So, fuzzy logic has 4 cornerstones. One is graduation, granulation, PRECISIATED, and what I have not defined as yet, generalized constraint. So to represent information, we are going to use the concept of a generalized constraint. So I showed this example, how we can graduate middle-aged. We have graduated earthquakes using the Richter scale. We have graduated hurricanes. We have graduated security alerts. But there are many things which we have not graduated. We have not graduated recession. We have not graduated of bear market and so forth. We have not graduated what we mean by mountain. So, strictly speaking then, we should graduate these concepts, but we have not done that as yet. So this is something that will happen in coming years. There will be a growing acceptance of fuzzy logic, and there will be a growing acceptance of the necessity of graduation when you talk about fuzzy concepts. So granulation then serves to make things simpler. Graduation serves to make things more precise. So, as I said earlier, granulation involves partition. So when you partition something with unsharp boundaries, we are granulating. Now, so quantization is a special case of granulation. So we can take age. Quantization is what you see on the left. Granulation is what you see on the right. You have young, middle-aged, old. So this is what I call the cause of linguistic variable. So well, that's what humans use. When they talk about age, they have an option of talking about age in numerical terms, but in many, many cases you use words. Young, middle-aged, old, not very old, etc. That is what humans use. And that involves what I call a linguistic variable. So, as I said already, we can take a function and we can granulate that function. And in that way, then, we come up with the linguistic description. We can granulate probability distributions, which is what you see here. I won't go into details here, but if you have probability density function, we can have some events, A1, A2, AN, which are fuzzy events, and we can talk about the probabilities of those fuzzy events, but the probabilities are also fuzzy. And then we interpolate. We ask, what is then the probability of an event A? And it's this sort of a thing that's used in reasoning with probability distributions. Now, here is an example of something that's used in practical applications. Honda fuzzy logic transmission. So you have rules, if-then rules, expressed in the natural language. So there are fuzzy terms like speed and torque and whatever the case might be. Speed is low. Okay, so low is a fuzzy concept. And then you define what you mean by low. And this is what I call declarative meaning. That is, you say, this is what I mean by low. And you give the membership functions of low. And then, depending on what the various variables are, then you take certain action, decision, which appears on the then side of the if-then rules. So if this and this and this, then something. So the designer of a fuzzy logic transmission then comes up with rules like that, and then he or she precisiates the meaning of fuzzy terms that are used in fuzzy if-then rules. That's the basic idea. Now, so we have then computing with words. And so this is the basic structure of computing with words. So we start with a question. What is the value of some variable? And then we have an information set, which consists of question-relevant information. And then we try to come up with an answer to the question. So to repeat then, computing with words has three principal components: question, information set, and answer. And the answer is arrived at through what I call aggregation function. So here is a simple example. The question is, what is Vera's age? Now here is the information. Vera has a son in mid-20s. Vera has a mother in mid-30s. Excuse me, has a daughter in mid-30s. And something that we draw from world knowledge. and that is that mother's age at birth of her child is usually between approximately 20 and approximately 40. Given this information expressed in a natural language, we want to come up with an estimate of Vera's age. And computing with words makes it possible to solve problems of this kind. And this is an important contribution to existing methods of computation. So computing with words is a system of computation which adds an important capability, a capability which traditional systems of computation do not have, and that is the capability to compute with information described in a natural language. So the information contained in information set is what might be called raw information. We cannot compute with raw information. We have to precision the raw information. So the first stage then is precision of raw information. We precision it when we come up with generalized constraints, which I'll have something more to say about presently. So translation into the language of generalized constraints is what we view as precision. And once we have these generalized constraints, then we compute. And we compute through constraint propagation. So this is the basic structure of computing with words. So the first phase is precision, cointensive precision, and the second stage is computation with precisated information. So here is simple examples. Young. We precision young when we give a fuzzy set which represents young. So this is precision of young. So young on the left side is raw information. And young on the right side, as a label of fuzzy set, that's precision information. But we can also move in the direction of imprecision. If I say Lily is 25 and I replace it by Lily is young, then I have imprecisated the information. So we imprecise information deliberately, in many cases, when there is a tolerance for imprecision, which we can exploit to reduce cost. Data compression is an example. So this is what I showed already. And so suppose we want to precision what they mean by approximately some number A. Well, the simplest one is A. Next one is interval, or we can have a probability distribution, or we can have a fuzzy interval, or we can have a fuzzy interval, etc. So there are many ways in which we can precision what they mean by approximately equal. But usually what we are interested in is something that is cointensive. And in most cases, a compromise would be a trapezoidal fuzzy set. Now, as I said earlier, we have to talk about generalized constraint. Now, we talk about constraints all the time, but usually the constraints we talk about are hard constraints. There is no elasticity. Generalized constraints have elasticity, and it's this elasticity that we need in dealing with natural languages. So what we have there is we have a constraint variable, capital X, we have a constraining relation, capital R, and we have a copula which tells you how R constrains X. And we have many different ways of doing it. We have possibilistic, veristic, etc., etc., etc. So little r is an indexical variable which defines the way in which uppercase R constrains uppercase X. So we have primary constraints, which are possibilistic, probabilistic, and veristic. Veristic has to do with truth, verity. Now here are some simple examples. Lily is young. How do we appreciate it? We say that what we have is a variable, capital X, which is the age of Lily, and we assign a value to that variable. But that value is a fuzzy set, most. So this is what we will call a possibilistic constraint and Mary's age. So that would be our precision of the meaning of Lily is young. Here is something a little more complicated. Most Swedes are tall. What are we constraining? What would be the proportion of tall Swedes among Swedes? That's the variable, X. And how are we precisating? Well, we assign a value to it, which is most. Most is a fuzzy number. So this would be a simple example of precision. Now, so there is a great deal more to be said about precision, but in the length of time that I have available for my presentation, I cannot do that, so I restrict myself to very simple, some very basic aspects of the concept of precision. And the same will be done in the concept of computation, phase 2. So what we're going to do is this. We are going to represent the meaning of a proposition or a predicate as a generalized constraint. Because basically, when we say something like Mary is young or Lily is young, we are constraining the values which Lily's age can take. And so, any proposition will be represented in that fashion. And when we reason, then, we propagate constraints. And what is used in fuzzy logic for that purpose is the extension principle. So, what we have then is this. We have some function of x, and we are constraining it by saying f of x is a, where a is a fuzzy set. And then we ask the question, what will then be the constraint on some other function, g of x, is what? What is that? The extension principle tells you what it is, and it reduces to the solution of a variational problem. And I won't go here into technical details, but in any case, what happens then is you come up with the answer, but that answer requires the solution of a variational problem. So here is a graphical explanation of what's involved. Now, so here is an example. I will skip the example. The example is in my presentation, and in case you are interested in my presentation, you can get it from the organizers of the conference, or by sending an email message to me, Zadeh at eecs.berkeley.edu, and I'll send you my PowerPoint presentation, in which this example is handled in detail. There are certain computations that are involved, and eventually you come up with an answer to the question, which is, what is the difference in the average height of Italians and the average height of Swedes? Now, so then let me come up with a summation of what I said so far. So basically, we are dealing with problems in which the information that you can operate on is imprecise, or more generally imperfect. That means imprecise, uncertain, incomplete, etc., etc. And that information is expressed in a natural language. Information be perception-based. If it is perception-based, then we take the perceptions, we describe them in a natural language, and reduce the problem to computation with natural language. So that is the basic idea which underlies the fuzzy logic-based approach to mechanization or formalization of human-level intelligence. So it's not the traditional approach in which you use classical logic and bivalent logic-based probability theory, but it is an approach where you use fuzzy logic and computational theory perceptions. And in fuzzy logic, as I mentioned a number of times already, everything is a matter of degree, and the degrees are allowed to be fuzzy. So what is needed then is a change in direction. What is needed then is a paradigm shift. You may recall that in the title of my presentation, I have a question: is it achievable? And so the answer is maybe it is achievable, but it will not be achieved through the use of existing approaches. What we need is a paradigm shift, which I sketched in my presentation. Now, I'm going to skip the rest. You have references to my papers. This is not references to the literature, just my papers. You want to study these things in greater detail. And also, there is a report in the appendix on the impact of fuzzy logic. And fuzzy logic, as I said already, has been, and to some degree remains, controversial. And many people have misconceptions. They don't recognize, they don't know that fuzzy logic is used in many, many products that they use every day. Digital cameras, TV sets, washing machines, microwave ovens, etc., etc., etc. And the reason it's why it's used in many, many consumer products is largely because of logic, fuzzy logic gambit. That is, you take advantage of the tolerance for imprecision, but then you impreciate first and you precision next. So imprecision followed by precision. In the end, it results certain advantages, particularly reduction in cost. And that is why fuzzy logic is used so extensively in computer products. You see that in the literature, there are many, many papers dealing with fuzzy logic, that is, papers in which fuzzy appears in the title, and it's growing. And there are many journals, and then I am somewhat pleased over the fact that there are many citations to my papers. Almost all of my papers are single-authored, but as you can see, the number of citations going up. For 2009, it's not complete as yet. So I wanted to thank the organizers of this conference for inviting me to participate in the conference, which I fortunately couldn't do, and to make this presentation. And I hope that perhaps I gave you at least a rough idea as to what is involved in trying to achieve something that is very basic, that is human-level machine intelligence. Thank you very much.